Well, hello, everybody. I guess we can get started. Today, we are delighted to have Stefano Campanella here, visiting from Trieste, Italy. He'll give us a special lecture. Stefano is a research software engineer at the National Institute of Oceanography and Applied Geophysics in Trieste, which is also the place where I did my PhD, so I really like it, and I'm excited to have him here. His research interests are in earth and environmental science, and especially computational oceanography, which I believe is something I'll talk about today. He completed a master's degree in high performance computing at system and is now doing a PhD in artificial intelligence. And he also has experience as a high school math and physics teacher. So obviously he doesn't mind being asked questions. So, I hope that you will take this as an invitation to ask him all the questions. And today he's talking about learning global ocean forecasting on hierarchical triangle mesh. So Stefano, welcome and take it away.
Okay. Oh, okay. This works. So thanks for the nice introduction. And yeah, I'll talk about our current efforts to build data-driven global ocean circulation model at our institution. And I mean, we already talked about me, so I'll skip on this, but my background is in physics. Then I moved to HPC to earth science, earth and environmental sciences. And I'm still huge programming language nerd. If you like functional programming languages like Haskell, Lisp, and Julia, I would love to have a chat afterwards. Oops. Okay. So a few words about our group. We are part of the oceanography division of the OGS. Our group is called Dynamics of Ecosystems and Computational Oceanography. We grew a lot in the last few years, mainly thanks to Next Generation EU funds. Nowadays, we are about 70 people, so quite a lot. And I would say that our main domain of expertise is marine biogeochemistry on a regional level, especially. But so lowest trophic levels, but also the higher one. We have expertise also in ecological modeling, for example, small pelagics, and etc. Here there are a few models we work with. Most probably you're familiar with MIT GCM. We do also a bit of Lagrangian modeling. But okay, so move on. What I will talk about. I will motivate a bit the need for yet another data-driven model. There are quite a few nowadays out there. Then I will give some details of the dataset we're using, and then delve into the details of GraphCast, which was the main source of inspiration for our model. As in the limits of these 45 minutes. Then I'll discuss the proposed architecture. So a little bit of a disclaimer. The inception of this project was rather circumstantial and I would say rocambolesque. We were working on a digital twin for the North Adriatic, a marginal sea within the Mediterranean Sea. But at the same time, we were working on, we were thinking about using graph neural networks to solve a performance problem in a super resolution applied to initial conditions for the model above. And we ended up landing on ocean modeling, physical oceanography on a global scale, because on many levels, it's an easier problem than biogeochemistry. So disclaimer, what I would like to say is we are still in an early development stage. Unfortunately, there will be no results I'll be able to show you. And I really consider this an opportunity to get feedbacks from talented researchers here at LEAP. So yeah, a little bit on motivation. Sorry. So subseasonal-to-seasonal timescales are a hot topic right now. Reason are that we don't understand them very well on one hand, and on the other, they're crucial for the decision makers. We know for sure that we would like to take into account all sources of predictability, and we would like to do probabilistic forecasting, because at these time scales, it really does make sense to make deterministic statements. And the community working on subseasonal to seasonal forecasting consider the ocean one of the main sources of predictability, and it's customary to run coupled ocean atmospheres simulations, although it's really hard to pinpoint in literature a single journal clearly stating in a definitive way what the role of the ocean is. Indeed, you can also find rather disturbing or disappointing results. Still, we would like to have a data-driven ocean model. And so let's briefly recap on data-driven modeling. So general recipe is rather easy. You write down your conservation and constitution equations, you discretize and solve them using a numerical model. Then you do data assimilation. That is, you reconstruct a coherent history of best estimates of your state. Then you train a machine learning time series forecasting model on that object area analysis. Hopefully what you get will have two main advantages. One is doing better than the numerical model you start with, since you learned on something that passed through data simulation. The other being extremely efficient. The reason is that if you implemented it using deep neural network, you'll take advantage of accelerators, which are really good at dense linear algebra. And here the plot is from the paper on AIFS, and you can see the analysis slowly catch up with the reanalysis, which has no incremental updates. The numerical model version is fixed. And then you'll see that there is a gap which you can quantify in quite a few years of development with using a data-driven model. So nowadays there are a few models out there. This is an opinionated and non-exhaustive list. Since we plan to talk about the ocean, I will not go into the details. But there are two interesting things to note. One is that the most grounded in theory model, the forecast net based on the Fourier neural operator, was, at least at the beginning, one of the worst performing ones. And the second is that these models have all different architectures. So most probably the inductive biases we're injecting, we're selecting with architectural choice do not matter that much from a machine learning point of view. So the data set is more important than the model. And
yeah, they have performance on this slide, sorry. So this is just date, lead time.
Yeah, I mean, somewhat implicitly, the reported lead times are the ones where the authors state that they have a skillful model. So because these are all autoregressive models, you can roll out indefinitely. And yeah,
like better effectively.
Yeah, it's in some sense, yes. And also they have different resolutions, but I mean, the point was to show the developments in this area. And also an interesting thing to note is the x-axis. All of this happened in 2 or 3 years at most. So what about the ocean? There, the situation is a little bit different. When you say weather forecasting, you're actually giving two pieces of information. One is that you're concerned with the atmosphere. The other is that the timescales you're interested with range from few hours to some weeks. And when you say ocean, it's completely it's a different matter. Indeed, we have models spanning from what in weather forecasting you would call medium range forecasts, namely GLONET, the model by Mercator, up to Samudra, developed here in the US, which you probably know more than me, which works on climate scales, decadal and more. So why do we need an ocean model on subseasonal to seasonal? Well, the idea is that there is always already one. It's called XIHE, but it's non-autoregressive, so it's not clear how to couple it with the atmosphere. And yeah, and also finally, what also the x-axis has a rather different scales with respect to the previous plot. These models were announced or published in the last year or so. So yeah, quite recent developments. And there is a lot of excitement around surrounding data-driven models. They got the cover of prestigious journals. But what I would like to point out is that I think most of the involvement of big of tech companies in the area is related to their high return on investment. These are models that are cheap to run, but also cheap to develop. Fewer developers, I mean, nothing compared to large general circulation models. So yeah, being that said, what about the data? So we start from Glorious 12, which is Notion and CI's reanalysis made at Mercator. It assimilates salinity, temperature, sea surface height, sea surface temperature, and CI's concentration. It has an eddy permitting or resolving is a matter, it's debated resolutions. Resolution of 1/12 of a degree and full depth down to 5 kilometers. Our dataset was regraded from Glorious 12 and 1/4 of a degree to ease the coupling with the atmospheric one. And also we selected the first 10 depth levels within the first kilometers, and this for two reasons. The first is that you're not assimilating data below that depth. So what you get there are basically model predictions. And secondly, the depths below the first kilometers really are not relevant for the timescales we're interested in. And yeah, there is one thing that I would like to point out is how would you treat the atmospheric forcings? At the end, we ended up averaging them, but since the datasets you can download from for example, Weatherbench have a 6-hour resolution. Here we have a daily resolution. There are a few strategies you could use. You can roll out your ocean model for 4 steps, and or you can somehow aggregate the values at finer time resolutions. And a little bit of a technical interlude. How would you store such a data set? This is non-trivial. At the end, we ended up using a multi-file dataset made of zipped ZARs, chunked along the lead dimension, the time dimension, with chunk size 1. This is crucial to leverage the parallel file system we had on our supercomputer, which is Lustre. Otherwise, and we were dealing here with files with sizes of about 10 gigabytes. I mean, you could use other strategies, but you would end up having really small chunks, which are useful for decompression, but then would pollute your parallel file system, in particular the metadata file system. So yeah, it would be really interesting to hear also how do you store your data sets for training these type of models. So a little bit of an introduction on graph neural networks. Try to be brief. So graph neural networks encode a specific inductive bias in the architecture, which is a relational inductive bias. But what is the crucial point here is that the type of such relations is particular to the graph, not to the architecture, which is rather general. So if you're dealing with social networks, it might be, I don't know, being friends on Facebook. If you are dealing with physics system, and also in particular in continuous systems, such as in fluid dynamics, usually what you encode is proximity. Nodes of the network are physically close by. And so a little bit, a few definitions here. We'll define a graph, a triple of three objects, a collection of nodes, a collection of edges, and global state. We attach to each of these entities an array of features, let's also called attributes. And our graph neural network will be a function approximator between two graphs. What I mean by that is that they take a graph as input and they return a graph with different values on their features, but the same shape. They'll not change the shape of the graph. And they have, here I'm following a really nice review by Peter Battaglia and others at DeepMind. And you can write down really the algorithm graph neural network in the rather general way by the usage of 6 functions, 3 update functions, one for the nodes, the edges, and the global state, and 3 aggregation functions. Based on if you're based on the exact shape and usage of this function, you can introduce also a taxonomy, and we will most be concerned with message passing graph neural networks. And in particular, with message passing neural networks where the global state is completely absent. So we will ignore that. And this is useful because something that is, I mean, not a piece of information which is not easy to find is a discussion of the memory complexity of graph neural networks. How much memory do you need on your GPUs? And I mean, we can at least estimate a lower bound by taking into account simply the input space. And as you see, the edge and vertices update function scales with respectively with the number of nodes and edges. And there is no scaling with the square of the number of nodes as you would get if you would use the somewhere in adjacency matrix. And this will come up later. So the important point here is that the main memory requirements come from allocating these large tensors. We will quantify how large they are.
Stefano, sorry, since you said questions are okay, can you go back and explain again what is message passing? Does it mean that you're looking at the message passing graph neural net?
Yeah, sure. I mean, the general algorithm is here. Basically, you start by updating the feature of each edge by using the previous value of the feature of that edge and the features of the sending and receiving node, plus the contribution from the global state. Then you aggregate on edges. By that I mean that you're interested in all the edges attached to a particular node and compute the new value of that node by means of this aggregated information. Here is the crucial point is that the aggregation function has to be invariant by permutations of the arguments, since you want to be able to relabel your graph and not affect the results. And yeah, and then you go on. So we said we already updated the value of the vertices, and for really for message passing neural networks without a global state, that's it, because all the other functions involve somehow the global state. Oh, well, that is interesting. For an example of application might be, for example, determining the energy of the fundamental state of a molecule. So it's a single number a single array describing the state of the whole graph, which might be something you can be interested in, make a prediction on, or take as input. I don't know, maybe if you have particles interacting among themselves, but also embedded in an external potential, the global state might encode that information. So yeah. And so a few words about GraphCast. So as many, I would say most of the models I've showed before, it's an autoregressive model. And it's 2D in quotes, meaning that the depth levels, the pressure levels here become features. And I mean, and this makes sense because we're dealing with a system with a high level of anisotropy. And also to use an encode process decode architecture where each of these components is a graph neural network. This is not mandatory. And indeed, the proposed architecture will not suffer from this. And finally, it uses an icosahedral multimesh, which we'll talk about in a couple of slides. So regarding the state, so they selected a subset of the available atmospheric variables, subsampled it subsampled the number of levels, and most interestingly, they use two past states to predict the next. These have become customary. Many models do that. Interesting thing, if you read the original paper, is that they determined it experimentally. Using two states, you would get better results than using only the previous one, but using more states would not have show improvements. And this is somewhat reminiscent of higher order integration methods, but most crucially, it's useful because you will never have three consecutive states within the same data assimilation window. So the model is constantly challenged. In ERA 5, they use 4D data assimilation, and so one of the three will be out of your data assimilation window. And okay, so regarding the encode process decode architecture, well, as I said, these three components are modeled using graph neural networks, and it's interesting to see how the associated graphs are defined. We will talk about briefly about the processor graph. The encoder is determined this way. You take a node of the processor graph and connect with an edge to it all the points in the grid which are within a ball of fixed radius. For the decoder, going the other way around, you connect a point of the grid to a node in the processor. If it falls within a triangle having that processor graph node as a vertex. It's a little bit involved, but I think that the diagram made it a little bit more clear. So being that said, we can say a few things about the icosahedral multimesh and then come back to the encoder and decoder. So the icosahedral multimesh is constructed iteratively. You start from a unit icosahedron, then you select the midpoint of each edge, connect them, these midpoints within a phase among themselves, and project these points and edges back to the sphere. So for each phase, at one refinement level, you will get 4 at the next. This is a really simple refinement procedure. Indeed, you can work out recursive relations, which allow you to compute whatever you're interested in, the number of nodes, of edges, and so on. So as you can see, the number of edges scales quite rapidly. And also, a crucial point is that the procedure I have just described is such that a node in a previous level of refinement is contained within the subsequent one. And this allows at the end of to squash all the meshes you got together and consider all the nodes of the finest refinement level and the edges from all refinements. So in the final multi-mesh, you'll get edges which comes from back from the unit icosahedron.
You are also quantifying the energy levels?
Energy levels. Energy levels of the states. What did I don't get the question? Whoa. I'm sorry. And yeah, I mean, yeah, there are physical considerations which will come here in this slide. So edges from the very first icosahedron are very far apart, like 7,000 kilometers. So they seem unphysical. And I mean, since you have a 6-hour time step, that would mean a signal traveling at more than 1,000 kilometers per hour, which seems not to be the case. And also, there is a really nice paper out that recently published on the fact that you'll get edges from the last refinement level and from the first, which are orders of magnitude apart. And apparently, the graph neural network struggled to learn scales. However, the original authors state that using a multi-mesh improves the performance, although I would say from the skill score, I would say mildly. And also the statement is rather incomplete since they consider only the edges from the last refinement and a multi-mesh including all the all edges. So
And for the short range interaction? You are presenting the long range interaction. What about the short range interaction?
Well, the short range interaction.
How do you present with your model? How do you handle?
Oh well, I would say. Okay, so if you can train the same model using only the last mesh with 6 levels of refinement, and then your graph neural network would learn only small scale interactions. And okay, so we can jump back on previous consideration on memory consumption and see that by the way we built the encoder, decoder, and processor graphs, the most memory consuming one are the encoder and decoder. The processor is negligible with respect to that. It's rather easy to do the math. I mean, because of what we told, the decoder will have 3 edges for each grid point. And so you can get a whopping 20 gigabyte of memory consumption for your decoder. And this is if you play around with the Colab notebook using GraphCast, the authors provide, that is what will make your session crash. So really few words about the loss. The GraphCast uses RMSE loss weighted on latitude, and also since this is a really multitask objective, weighted on features with empirical coefficients. And I mean, the loss has known limitations, but honestly, the first paper where I've seen simple mathematical argument for this case is the one by Tobias Sells and others, which I'm showing here. And so using L2 norm will imply a reduced effective resolution for your data-driven model. interesting thing is that apparently you can recycle your architecture as a denoiser in a diffusion model, as they did for GraphCast. But if you're interested in data-driven deterministic models, that is something to take into account. When working with ocean data, also you have the bathymetry, so somehow you have to deal also with that. So a few words about the training curriculum, because also this will be interesting in light of the proposed architecture. So they use a pretty standard warm-up cosine annealing training schedule. The original contribution of behind GraphCast was using these autoregressive steps. Was optimizing when doing optimizing longer trajectories, which effectively is backpropagating in time. And an interesting thing to note also on memory consumption is that if you use longer and longer trajectories, then you'll have to store the state of the system and the predictions, which contribution of which becomes on longer trajectories comparable with respect to graph neural networks memory requirements. And also another thing is if you do the math, they needed about 8 seconds for gradient descent iteration. And unfortunately, I cannot report the exact numbers, but the I/O is a non-trivial part, non-negligible part of that 8 seconds, and that and this is the reason why I was asking for about your experience with handling such data sets. So to recap, things we don't like about GraphCast. Things we like about GraphCast: the icosahedral multi-mesh takes automatically into account the topology of the domain, which is rather different from other architectures taken from image processing. You can circle around the globe both along latitude and longitude dimensions. It has public code weights and is extensively documented and still state of the art, although being a few years old nowadays. But there are things we don't like. It has this symmetrical symmetry built into it, which is not the case if you have land points, land masses, sorry. It has a rather memory-heavy encoder and decoder. And also, the autoregressive steps can eat a lot of memory. So how do we propose to solve the problem? Well, we're working on an architecture capable of switching between a Cartesian grid, the one on which GraphCast is trained on, and a triangle mesh, the one that would be more would you use for a complex domain, probably more in a more immediate way. And then we will see you have the problem of reintroducing these long-range interactions, and for that we'll use a hierarchical triangle mesh. So, but first thing first, there was an option. There is an easy option, which is to just mask the land points in your processor graph. Not exactly all. Okay, so the picture is not very well displayed, but probably you get the gist of it. You'll have to retain some land points because of how the decoder works. Remember, you connect with an edge, a grid point to the 3 nodes in the graph of the triangle the grid point falls within. And this strategy has advantages. This non-parametric. You don't have hyperparameters to tune for your mesh, and requires only minimal code modification. So it's really easy to run experiments on that. It has advantages, however. You will lose many of the nodes of the multi-mesh graph, which had a lot of connections, a lot of edges, and so these long-range interactions. First and foremost, you will have a poor modeling of the coastlines, and you will have a fixed resolution on all the globe. While in ocean modeling, we would like to have a varying mesoscale size as you go into open ocean and far from the coast. So what about using a full-fledged ocean triangle mesh? Meshing is, I would say, more an art than a science, but there is a lot of literature on the topic, although there are not that many finite element method global ocean circulation models out there. For an isotropic mesh, you will need just a single scalar field describing the target mesh size for each point of the domain. And this is built using usually taking the minimum of several criteria, so a collection of scalar fields. In our case, we just need once because we are not developing a numerical model. So for example, the bathymetry is not taken into account because we don't need to dynamically resolve gravity waves. And this approach has advantages, since we solved the previous two problems. But as I was saying, we have no long-range interactions. And also there is a bit of parameter tuning because it's non-trivial to have a mesh of the whole ocean. By the way, I really recommend the package by Lambrechts at University of Leuven, C-Mesh, mostly based on G-Mesh, if you have experience with it. So, but this leaves open the question: how do you switch between a Cartesian grid and an unstructured grid? So we'll borrow a couple of concepts from finite element methods, although without all the theory behind them and without being too formal. I apologize to the experts in numerical analysis in the audience, and also for the sake of the argument, I will illustrate with examples from in a 1D domain. But the arguments goes the same way. So we have a function we would like to define on an interval of the real line. We would like to approximate, and we can sample it on at regular intervals, and that would be our Cartesian grid, or on unevenly distributed points, and that will be the non-structured mesh, non-structured grid, the mesh. So in finite element methods, they when they're discretizing PDE, they're restricting the solution to the span of a finite number of functions with compact support. Usually they're polynomials of fixed degree, which define values on the nodes. In particular here, we will consider linear functions defined on elements, having the nice property that their value is 1 on the having the nice property that there is a one-to-one correspondence between mesh nodes and basis functions, and the value of this basis function is 1 into the to the node they correspond to, and 0 on the other. So these are piecewise linear functions, which in the 1D case are the triangle shaped. And so say as we said, we're restricting ourselves to linear combinations of these objects. So say that the value of this linear combination is prescribed on a mesh node. because of the property just told, it's easy to convince yourself that the coefficients of this linear combination are just the values on mesh nodes. But now, what about if I want to compute the value of the function on a point which is not a node? Well, as we told, is just a linear combination. We know the coefficients, and so we only have to compute the values of the basis function on that point. Only a fraction of them will have non-zero value, since this function have compact support, and they're non-zero only on elements sharing that sharing one node. And yeah, so you can easily compute the value of this linear combination for arbitrary points, in particular for all the points of the original Cartesian grid. And yeah, so if you have your fields defined on the mesh, it's really easy to go to the Cartesian grid. What about the other way around? Basically, you have to solve a linear system, which, depending on the number of grid points and mesh nodes and their relative positioning, might be over or underdetermined. But you can always solve it in the least square sense, and so get the best piecewise linear function that interpolates your that pass through your points. And so finally, we can use this in the architecture. You start from the fields. You start from ocean state defined or Cartesian grid. You fit that onto the mesh node, and now you have physical variables defined there. Now you have to embed them in a latent space representation. And you can do that with using a simple MLP. So the rather complicated graph neural network that worked as a decoder in GraphCast now is a rather simpler component. Now you can run your message passing steps on the processor graph, which is the mesh. And after and having in hand the predictions for the next time step, you can project back the solution onto the original grid. Now, the interesting thing is the following. Of course, you can compare with whatever Cartesian grid. You just have to recompute the value of those basis functions in different points. And also, from a computational point of view, you'll just need to do it once. After that, you just have to store a matrix, which allows you to go from one to the other. And yeah, and you can even roll out steps within the on the mesh, which has far fewer points. So your state space, the size of the state space is quite reduced. And also, the code step is fully differentiable because you're simply doing a matrix multiplication. The fitting the original grid onto the mesh is in general not, but you will not need to differentiate because it's non-parametric. You're just doing least square fit. And so, but we thought we lost along the way this long-range interaction. How would you solve the problem? Well, the usage of graph neural networks for continuous systems and in fluid dynamics in particular has literature on it. And so you could use what they call multi-scale mesh graph nets, which are somewhat analogous to multi-grid methods in finite element methods. the idea is that you start from a high resolution mesh, you do message passing steps there, then you downsample to a coarser mesh, which will model your long range interactions. And you can do that using the same strategy we illustrated for GraphCast. So it's just a matter of connecting the edges using the previously illustrated rule. Then you can do message passing steps on the low resolution one, and finally project back to the high resolution mesh. These these multi-mesh, multi-scale mesh graph nets have quite good performances, at least in fluid dynamics. But there is space here for I think a small detour, because as I said, you can encode the type of relation you are encoding in the graph is not peculiar of graph neural networks. So, for example, there is a whole field of study called climate networks, where basically you fill which has been used mostly for diagnostic purposes, and allows you to model other type of inductive biases here. What I'm saying is your low resolution, it's up to you how to build the low resolution graph. And so this leads me to the conclusion. Really hope to have not bothered you too much. I'm really hoping for
Thank you so much. Any questions in the room, or if anybody on Zoom has a question, feel free to unmute yourself.
Very interesting presentation. I have a question. When you have the data sets that you are training your model, some of the data sets points have different grids. How do you handle that? Let's say you have some grid in the middle of the ocean and one data set at the interface between the continent and the ocean. How do you handle what is your idea about how do you handle if the data sets that you are training your model are not uniform?
Okay.
Which function are you using? Because you are just fitting.
Okay, so we're working here with a single reanalysis, which has a coherent grid. And we regridded it using a conservative algorithm at 1/4 of a degree, at least for state variables. For the bathymetry, you have to use like nearest neighbor. And this is the same grid that, for example, atmospheric forcings use. So, I mean, all state variables are defined on the same grid, starting grid. But using this least square fitting procedure, you can use different data sets without having to regrid them on the same grid. And this is an interesting topic. I mean, from an engineering perspective, would you go for fitting the whole data set beforehand and storing that, or trying to do this least square fitting at each every time your data loader hands you a sample? Because in that case, you have to overlap the computation because it can take a while. So it's an interesting data loader engineering problem of how to handle this. But yeah, I mean, I've not commented the numbers, but you can have quite nice global ocean mesh using less than 50,000 points, which is far less than 1 million grid points you would have for the starting data set.
How do you minimize the computation time?
Well, yes. To minimize the computation time. Oh well. Oh, well, for predictions is not, for making forecasts is not a problem, since you need just to do this conversion for the first two states. Then you can roll out iteratively for as long as you like and project back on the grid using sparse matrix multiplication, which is cheap. For training, I mean, this is something to think about carefully. Yeah.
A great talk, very interesting. I was curious to get maybe your thoughts, so it's very flexible, the graph structure, especially for the ocean, it makes a lot of sense, maybe for the atmosphere, you could argue as well. I'm just curious about your thoughts, especially when you start thinking about multi-scale, especially when you get into the realm of like transformers and all that. So some of the architectures are actually quite nice, when you go beyond graphs, so what are kind of the advantages you see and maybe some of the drawbacks? I mean, you mentioned, especially thinking about the multi-scale perspective, in space and time, so where I'm coming from is that I feel that sometimes the graph, I mean, they are very nice in structure, but in terms of the developments, there are a few months or years behind like what is happening in like computer vision and things like that, for like regular grid, for instance, or time series, for instance.
Yeah. So I think there are many nice architecture out there, the development of which, however, is driven by, for example, image processing, which have rather different needs. I talked a bit to Anas Elaouni, the author of GlowNet, and so I cannot point, it was a private communication, I cannot point to a precise paper, but most of the problems you have, the system will blow up because it is accumulating error on the coastlines. So that motivates the usage of graph neural networks. With respect to other architecture, a nice thing to point out is that these are rather data efficient. GraphCast is about less than 40 million parameters, which is way different from architecture employing some attention. And indeed, even basically the number of edges and number of nodes becomes basically a batch dimension in learning these parameterized update function. So even seeing a few samples, this function have several, because the point is that you're trying to learn local interactions, and this is, I mean, maybe it's because I'm a physicist, but this is really seems a nice property of these objects.
Thank you.
Hi, Stefano. Thank you. Very nice presentation. So the multi-scale grid you mentioned before catches my attention. So I will ask you to expand more about this multi-scale representation, multi-scale grid, and if that means that your loss function is multi-scale, and how you can extract this multi-scale representation, and if the information you obtain at different scales is in some sense orthogonal, in the sense that you are not focusing on like the same information, right? So you obtain a multi-scale representation that it is in practice orthogonal, so the information not overlap from scale to scale.
I see. Honestly, I haven't thought about that. I think, for example, the main source of interest in that is an observation by Ryan Kiesler, which empirically found out that you get better skills if you train your model on increasing resolution targets. And this type of architecture made this really easy. You just have to project back the results on different scales. but yeah, it's something one can delve into, because yeah, there is different scales provide different information. So
but having these scales means that you penalize the errors at different scales. So your loss function should be properly adapted to handle this multi-scale representation, or it is just something that you have in a latent, you have like the latent representation, but in the end you project back into the original space, and your loss function is somewhat traditional one.
Yeah, no, honestly, we plan. I mean, our first experiment, which hopefully will be in the few months, in the next few months, use start from GraphCast and use a simple 2 norm. But yeah, this is something to think about.
Yeah, think about, because I think the multi-scale representation is something really interesting.
Yeah.
So thank you.
As long as it's, I mean, differentiable, you can backpropagate fully.
Yeah.
I mean,
yeah.
You
can like use traditional loss, but the way you extract the information at multiple scale can be like something fancy, but you can stick with so traditional loss function, but at multiple scales, right?
Thank you, Stefano. Very nice. I have a very simple question, which is you mentioned why, like you moved on from a Cartesian grid to a triangle grid, saying that it was more appropriate for this problem. Can you explain why? Like, what's the advantage of using the triangle?
Oh, well, yes. I mean, we started thinking about graph neural networks when, because one of our colleagues, which was working on super resolution applied to an initial condition of our model for the Adriatic Sea, I mean, she had a performance problem because you're wasting 30% of your points storing nonce, basically, because of the land points. And also, she was getting really strange results when trying to interpret the results. If you, for example, if you I'm not an expert on explainable AI, but for example, if you use integrated gradients or other techniques like that, she was seeing that length points storing no information having much affecting the water points. So being able to completely eliminate the land for the simulation was, was interesting.
This is something that you can do with the triangle. You don't have the same masking issue. You just change the shape.
Yeah.
Okay, I see.
Yeah.
I see.
Yeah, you don't have to mask because and I mean, you cannot blame UNets for seeing spurious correlation between the two things, because they're convolutional networks, and so they learn local interactions as well. And you're applying that on water and land points as well. So they get understandably confused, I suppose.
Okay, we have a question on Zoom from Akila. Thank you for your presentation. I am curious to know, is message passing between the edges and nodes based on relationships between the variables, for example, cause and effect?
Oh, yeah, I see the point. If message passing represents physical interactions. Well, definitely, as I was pointing out before, if you have really far apart nodes, that seems unphysical. But for the rest, I would say that, as is often the case in machine learning, it's hard to interpret what exact type of relations are learned.
Okay, great. So we are pretty much at time, but are there any other questions in the room or on Zoom that anybody wants to ask before we conclude? Okay, thank you so much.
Thanks.